Hello and welcome everyone to this course on Bayesian Data Analysis. So as said earlier, I'm Oscar and I'm going to be your teacher in this course. To start, I will make these short videos making a recap on basic elementary knowledge and principles on probability, random variables, and also distributions. But also I will make a short review on current state of statistical inference. We will overview the replication crisis and how the statistical inference has played a key role in all of that phenomenon, and maybe the ways forward can be also relying on statistical inference, and maybe Bayesian inference can play a relevant role. So to start easily, I will make a small recap on probability. So first of all, I want to remind ourselves that probabilities are continuums, and our minds normally deal harshly with continuums because normally they tend to think in categories because they are easier to manage. These categories are mostly arbitrary, so as you can see here in this continuum of colors, I would say that the blue stops here and then starts purple, and then the purple stops here and starts pink. But maybe these arbitrary categories from myself could be insufficient for a painter or someone that is trained in visual arts and will have a lot more of categories to be precise and specific with the colors that we can have. And also, if I'm a physician, would say that some shades of brown, yellow, and blue can be very important and very relevant to each job because a shade of yellow in a skin could indicate a liver failure, and also a shade of blue in a skin can indicate choking, for example, or grave danger. So therefore, these categories are mostly arbitrary. In addition, it's important to remind ourselves that the mind also is looking for patterns, to the point that we many times see phantoms of patterns that aren't really there in pure randomness because they are not perfectly uniform. That's the typical example in cognitive psychology when they need to present some stimuli and they need to create pseudo-random series of stimuli to ensure that the participants are not getting trapped in the illusion that they are getting some patterns over there and they need to react to them. Okay, so in addition to this, we also have some heuristics that process information and probabilities also, for example, anchoring. So these heuristics are a fascinating field of research, and we can create really simple illusions, for example, like this one, when many people would say that from these three series of genders of babies, the third one would be the most likely because it appears to be more random than the second one or the first one when they are basically equal because they are independent events. Okay, so in addition to this, we can create a lot more of simple illusions. For example, probabilities inside a category, for example, low, and can be read as more proximate between each other compared with probabilities from another category that can be, for example, high probabilities. So we need a more rational approach to this. More completely, we need to train our minds to avoid these heuristics and also use statistics and probability to guide us. Okay, so what they are talking about in probability and statistics? Okay, so really quick recap. We have random experiments that are situations that cannot be predicted with absolute certainty. These random experiments have elementary events that are things that could happen. The sampling space is the space where all of these possibilities can happen, and a random event is a subset of this sampling space. The occurrence of an event is that the random experiment is one of these elementary events, and the verification of an event is the result of this experiment coinciding with some of the events. When we have probabilities of something, then also we can do operations. For example, the probability of something and its complementary, that is everything that is not this event. We can also calculate union of events, that is the probability of something or other thing to happen, and also can be easily calculated. We can also calculate the intersection of things, that is the probability of two or more things happening at the same time, and also condition probability, that is the probability of something knowing that other thing has already occurred, that we will elaborate more on that later. So, how we can calculate the probability of something? This is a typical thing that we tell our students about the approaches of probability. Okay, so the classical approach assumes indifference of events, and therefore they can assume that the relative frequency, that is the number of times that an event has occurred divided by the number of total events on the random experiment, is the probability of an event. Therefore, it's going to be a number between 0 and 1. 0 is impossible, and 1 is absolutely sure. And the probability of something added to its complementary is always going to be 1. The second approach is the typical approach that we use in statistical inference, that is called the frequentist approach or the relative frequency approach. This approach does not assume the indifference assumption. Therefore, we assume that it's not possible to know how many successes we need for each event, and therefore the probability of success is also going to be the relative frequency, but is depending on the number of times we repeat the event or the random experiment. Therefore, if we can reach an infinite number of repetitions, therefore it's going to be 100% sure this relative frequency, but as we cannot get to the infinity, we are always going to be in an approximation. This is a visual representation. I think is very intuitive. So as you can see here, if we increase the number of flipping coins that we can have, the proportion, the relative proportion of getting heads slowly starts to converge on the true value of the probability of getting heads, that is 0.5. So this is the typical approach of the frequentism, and also is the foundation of the sampling distributions, because if instead of tossing coins, we are gathering a sample to calculate its mean, therefore the sampling means are going to be also an object of probability, that they are going to slowly converge on the population mean, and the variance of these samples are going to be narrower and narrower each step as we have larger samples. So they are going to be more precise on the population value. Okay, so just this quick recap, very quick. I want to stress one idea that is going to be important. That is that these two approaches assume that probabilities exist by themselves. They are essentially apart from the subjects that are observing them. In most cases, these approximations will allow us to approach the true probabilities with some error. Okay, so that's everything from now, and we will continue moving on.